Alright, silly people, here's the situation. Uh, we are solving the differential equation which describes a object falling through the air um, subject to a linear air resistance uh, in an analytic way rather than in a ponderable way. Uh, so um, already we have it written like this, so we can go ahead and turn this into a couple of integrals. On the left side, we're integrating dvy over vy minus terminal velocity, and these integrals also have bounds on them. Uh, on the left-hand side, we're integrating from the initial velocity to the um, velocity vy at time t. So I'm going to use this notation where the vy prime inside of the integral is a variable vy. Um, so that's that integral. On the right hand side, it's minus b integral from 0 to t dt. Um, so on the left hand side, we're going to want to use a u substitution of vy prime minus the terminal velocity, um, so that du is just the same as dvy prime. And you see that this integral is pretty much just du over u, which we know evaluates to natural log of u. And on the right hand side, that evaluates to minus bt. Um, Moving m to the left side and evaluating the left hand side integral, moving n to the right hand side, um, it's the natural log of vy minus v terminal, that's vy prime, um, evaluated at points v not y and vy, and then it's minus b over m t, right? So just evaluating that at the bounds, we'll have a natural log of vy minus v terminal up top, and then a v not y minus v terminal on the bottom is minus bt or m, and we can raise both sides up to e. So on the left hand side, you're just going to be left with what's ever left in the natural log, and then on the right, you'll have e to the minus bt over m. And then solving for vy, you'll get v terminal plus v not y minus v terminal, e to the minus bt over m. And then once you make the substitution of the definition of tau as being m over b for the linear friction situation, you have v ter plus v not y minus v ter e to the minus t over tau, which is exactly what Taylor got in equation 230. So it works for me.